Hello students, in the last lecture I discussed about electrocardiogram. So what is electrocardiogram? It is the graphical representation of the summation of bioelectric potentials that appear at the surface of the body because of the heart muscles. So that was electrocardiogram. And in this lecture I am going to discuss about electroencephalogram. So basically what is electroencephalogram, or you can say EEG, electroencephalogram, or you can say EEG, that is EEG. So what is electroencephalogram or EEG? So basically these are what happens inside the brain. Also we have numerous nerve cells, and these nerve cells also generate bioelectric potentials, and when these bioelectric potentials appear at the surface of the scalp, when these bioelectric potentials appear at the surface of the scalp and we use a measuring electrode to record these bioelectric potentials, then the graphical representation of these bioelectric potentials that we get is the electroencephalogram. Or in very short term, or in a very precise way, if I have to say what is electroencephalogram, it is the graphical representation of summation of bioelectric potentials generated or produced by the nerve cells of the brain, or you can say generated because of the neuronal activity of the brain. Now as you can see in my previous slide here, this is the electrocardiogram that I have explained in my last lecture. So as you can see, in electrocardiogram we have designated each of the point of the electrocardiogram, that is we can recognize each and every point of the electrocardiogram. We can recognize that this point is occurring because of this activity of the heart. But in case of electroencephalogram, the graph that you will get, you won't be able to recognize it that way. It is a very complex pattern. As if I show you the electroencephalogram graph, this is the graphs of electroencephalogram. As you can see, the graphs are so complex that we cannot recognize it completely, or you can say we cannot recognize it totally as we used to do in case of electrocardiogram. In electrocardiogram we can recognize each and every point of that graph. So now one more thing, in case of electroencephalogram, what I told you how we get electroencephalogram graph. We get the graph by using the measuring electrodes. So we have to use the measuring electrodes over the scalp of the human body, over the scalp of the over the scalp. If you use measuring electrodes, then you can record the electroencephalogram. Now depending on the location of the measuring electrodes, depending on the location of the measuring electrode, that is on any portion of the skull where you're actually putting the measuring electrode, depending on that you will get different types of electroencephalograms. So these waveforms of electroencephalogram, they varies greatly with the location of the measuring electrodes. As you can see, these are the graphs here. These are the typical human electroencephalogram, and these are the 8 tracings. These are 8 tracings, like 1, 2, 3, 4, 5, 6, 7, 8. Here I have shown 8 tracings, that is 8 electroencephalograms, and these tracings indicate the region of the scalp from which each channel of EEG was measured with respect to one of 2 reference ear electrodes, A1 and A2. As you can see, this is the scalp of the human. This is the scalp of the human, and these are the reference electrodes, either A1 or A2. So taking A1 or A2, you can take any reference electrode like A1 or A2, and these are the measuring electrodes location over the scalp. So you can choose any location, and depending on the location of the measuring electrodes for the same situation under the same condition at the same time, if we use measuring electrodes at different areas of the scalp and the reference electrodes either to be A1 or A2, you will get different electroencephalogram waveforms. So these are the different electroencephalogram waveforms. So as you can see, like F7A1, what it is representing here, F7, the measuring electrode is at this position of the scalp, and this A1 is this, the reference electrode is this A1. The reference electrode is put here, and this is the measuring electrode. Similarly, by putting the measuring electrode at F7 and reference electrode at A1, we got this electroencephalogram graph. Similarly, for if you see the second tracing, that F8A2, what it is representing? It is representing that the measuring electrode is at F8 point, like the measuring electrode is at here, and A2 is representing the reference electrode. This is the reference electrode. So if you put the reference electrode here and measuring electrode to be here, you will get a electroencephalograph waveform like this for a particular situation. So these are for the same incidences at the same time taken for different location of measuring electrodes. Now experiments have shown that the frequency of EEG waveforms, you can see these are the EEG, and now the frequency of this EEG waveforms, they get affected by the mental activity of our brain. So how I'll show you certain characteristic EEG waveforms. These are the certain characteristic EEG waveforms that I am showing here, which are related to sleep, and how the mental activity of a person is actually affecting the frequency of EEG waveform, that I'll show you in this slide. Again, I am repeating how the mental activity of a person is affecting the frequency of EEG waveform. I'll be showing you here. So these are the waveforms that are related to sleep. These are the characteristic EEG waveforms related to sleep. So if you okay, now for every point like A, B, C, D, E, F, we have two waveforms. Like for A, we have two waveforms. Then for B, we have two waveforms. Then for C, two waveforms. So what these two waveforms are representing? So these are in each case, this upper record, this upper tracing is from the left frontal region of the brain, and the lower tracing is from the right occipital region. That is, it is showing the two different position of measuring electrodes for the same situation. Now coming to the main point, how mental activity is affecting the frequency of the EEG waveform. Let's see. So when a person is alert, when a person is in alert situation, like when a person is wide awake, he knows everything, he is doing some mental activity, then at that time the EEG waveform, the frequency of EEG waveform will be unsynchronized, and it will be very high, that its frequency will be above 13 hertz. The frequency at this position will be above 13 hertz, and it will be in unsynchronized very high frequency. Now if a person is in drowsy state, like very drowsy condition, if a person is in drowsy state and particularly the eyes of the person are also closed, then the EEG waveform that we will get for that person is this B. So as you can see, the frequency is comparatively less or smaller or comparatively less as compared to the point A. Here the frequency is in point B, here the frequency is between 8 to 13 hertz, and it is in synchronization. As you can see, the waveform, the frequency is in synchronization, and it is like the natural frequency of the brain. Now next point, that is the C point. It is representing, what it is representing, when the person is person begins to fall asleep. What happens when the person begins to fall asleep, and what happens at that point? The frequency starts decreasing. So what is the relation? When the person is in very high mental activity, the frequency is very high of electroencephalogram waveform, and when the person is in drowsy state, the frequency decreases, and when the person starts going to sleep, like when the person is in light sleep, then the frequency decreases further and the amplitude increases. You can see the amplitude is somewhat greater than the previous two waveforms, and the frequency is also it is decreasing. The frequency is also less. Now as soon as the person goes into the deeper sleep, you can see the amplitude keeps on increasing and the frequency keeps on decreasing. So this is how amplitude and frequency gets affected by the mental activity of the brain. Now what happens? Now the person is in a very deep sleep. So this is the condition where the person is in a deeper sleep, and here you can see the amplitude is higher and frequency is lower. Now there are certain times when a person is in sound sleep, all of a sudden the EEG waveform, whose amplitude should be greater and frequency should be smaller, all of a sudden what happens? The frequency gets unsynchronized and gets very high. The person is in sound sleep condition, but at a certain time what happens? If we measure the EEG, if you record the EEG waveform of that person, at a certain time you will get to see that the frequency gets unsynchronized and very high. So this state is referred to as paradoxical sleep. This state is referred to as paradoxical sleep, because here the EEG waveform is more or less like the person who is in alert or awake condition. So another name for this is rapid eye movement sleep, or you can say REM sleep, rapid eye movement sleep. And here the rapid eye movement, it does not so this rapid eye movement sleep, you can say the person is dreaming. So the eye under the eyelids, the movement of the eyes are very rapid, which means the person is in dreamy state. So when the person is sleeping, and when you get to see that the eyelids of that person is moving rapidly, the person is in sound sleep, the eyelids of that person is moving rapidly, at that point when you will record the EEG waveform of that person, you will get to see that it will be like this, that is, the frequency is very high and unsynchronized. So it is related to the dreaming. Now there are various frequency ranges of this EEG waveform which have arbitrarily been given the Greek letter designation, because these frequencies seem to be the most prominent, as you know that the frequency seems to be the most prominent feature of the EEG wave pattern. So as I've told you, how the frequency gets changed because of the mental activity. So from this you can conclude that the frequency of the EEG waveform is a very prominent feature, and there are various frequency ranges of the EEG waveform which have been given the Greek letter designation. Like above 13 Hz frequency is given the name beta. So as I've told you, when the person is when the person is in alert condition or wide awake, then the frequency is greater than 13 Hz. So we can say the frequency is beta. And then in the next slide you can see from about 8 Hz to about 13 Hz the frequency is alpha. So as I've already told you, when the person is in drowsy state, the frequency range varies from 8 to 13 Hz, which means this is the alpha frequency. Similarly, we have theta and delta frequency. Delta frequency corresponds to the frequency which is below 3.5 Hz, and theta frequency corresponds to the frequency from 3.5 Hz to about 8 Hz. So these are the different frequencies of the electroencephalogram waveform. Now, experiments in biofeedback have shown that under certain conditions, People can learn to control their EEG patterns to some extent when information concerning their EEG is feedback to them either visibly or audibly. That if a person is able to see his EEG pattern, then depending upon that reaction, he or she can control the EEG pattern. So this is the biofeedback. So I'll tell you when I'll be explaining this chapter, there I'll tell you in very clearly about this topic. That is how in biofeedback EEG patterns can be controlled. Moreover, as indicated, the frequency content of the EEG pattern seems to be extremely important. In addition, phase relationship between similar EEG patterns from different parts of the brain are also of great interest. As you can see, these are the two waveforms from the different parts of the brain for the same situation. So if anyhow we can measure the phase relationship between these similar EEG patterns from different parts of the brain, then the information of this type may lead to discoveries of EEG sources, that is electroencephalogram sources, and it will hopefully provide some additional knowledge regarding the functioning of the brain. So this was all about electroencephalogram. In my next lecture, I'll be discussing about electromyogram. That is, these are the graphical recording of the bioelectric potentials which are associated with the muscular activity. That is electromyogram. So I'm ending this lecture here. Thank you.